Hello, ma. Screen is visible?
Yes, sir.
Okay, Nan. Here, in this unit, it is a finite automata means it is a any missions. Missions, it is we will be whether we have a connection or not. In that connection, it will be the connected. Then we can be clearly we can say that it is we have a is connectivity finite automata theory. Output is comes to means it is a one. Indication is one, and output is not come means it is a zero. So and zeros and ones in representation, which will be the when that is the nature of the connections will be the connected. That is systematically is called as the automata. In that automata, finite number of the set of elements, how it will be connected to the finite number of the set of elements. That means that is any circuit board will be there. For example, it is a TV will be there. In that TV, it is a circuit will be there. One circuit will be connected to the another circuit board. It is a different connections. So like it is a how many connections are the passing the signals to the one place to another place. Such a kind of the connectivity is a observation is called as a automata. That functionality here we will discuss here. It is a finite set of the elements. If we take that is a finite automata, and we have a syllabus in the finite automata only. Now it is a deterministic and non-deterministic. Two types of the finite automata theory will be there. In that it is a DFA means it is a equivalence of the deterministic finite automata. DFA means it is a deterministic finite automata. NFA means it is a non-deterministic finite automata. And Morley and Melly missions. Here they use it that is the missions. It is all the missions cases how it will be the signals will be the passed. That is only the criteria here. So it is a Mori and Melly. It is they developed that is the finite automata theory connections with the missions. How it will be the signals will be the presented in the minimization of the finite automata that we will be, and the turning missions also we can be applied. This is our oral idea about it. Define that is a DFA, deterministic finite automata, and the non-deterministic finite automata. And define that is it is the concept of equivalence. DFA, deterministic finite automata, and non-deterministic finite automata, Mill and Morley missions, and it is a define the minimization of finite automata. These are the three concepts we will discuss today. And here it is in this theory computation, it is non-deterministic finite automata, finite automata. It means that is the finite state of the mechanism in that mission. So how it will be the allocated, where for that is each pair of the state and input signal symbols, each pair of state and the its input symbol, input what you are getting, output what are the output we can be get it, that is the input symbol we are representing, and where the for each pair of the state here from the here to there connection, that is called as each pair of the state. Now it is a NFA means it is a non-deterministic finite automata. What the first introduced by the Michael O. Robert and the Donna Squat in the 1959, and observed the NFS are equivalent to the DFA. Year 1959, it is observed that it is a non-deterministic finite automata and a deterministic finite automata, both are the equal. And it is after that certain days, it is after that concept, it is provided certain results in the theory of the computation. In the computationally, they observe that it is a they are the both are the bifurcated. It means that it is a deterministic, it is a non-deterministic is a choice of the moves of the automata, and instead of the prescribed the unique move to the each situation. We allow the set of the possible moves. This is this we arrive by the defining the transition function. What is the moment having that function is called the transition function, such that it's the range in the set of the possible states. It is a if the signals, if we give that, it is a what is the range, that range is a set is a possible states, how many we have, how many states we can be give it. That is the information we can get it. Then NFA, non-deterministic finite automata, that range of delta the transition function, it is a power of the 2 to the power of q, 2 to the power of q power states we can be functional transformations we can get, that is the states, and its the value is not a single element of the q, but it is a subset of it. Now, in this unit, we also introduce the concept of the equivalence of the two computationals. Also, it is a DFA and the NFA. We also design an algorithm to construct a finite automata with the minimum number of the states, which is a connection output. We want to get it with the minimum number of the connections. That is only the minimum number of the states equivalent to the given automata. How much connectivities we have. Finally, we introduced this is a turning mission. The simple mathematical model of the computational design is a aligned turning he has given. That is a turning missions. Non-deterministic means non-deterministic finite automata. It means that it is a non-deterministic finite automata is a uh, uh, quintuple. Quintuple means it is how many we have: q set and sigma and a delta q naught f. All five parameters will be involved. In that is a quintuple, and we call as a quintuple, where the q, sigma, q naught, f are defined as a deterministic finite automata. Delta mapping only it will be the changes, that is a total perception, so that it is called as a delta is a pi cross epsilon to 2 power q. So that's why it comes to the non-deterministic finite automata. Now, main difference between the DFA and FA is only in the delta. For the DFA, the output now again. Mala search paper kipodu. The main difference between the DFA and the NFA is only the in delta. For the DFA, the outcome is a state and a element of Q, whereas for the NFA, the outcome is a subset of Q. Like the DFA and the NFA, the DFA, NFA also can be represented by the state tables and transition graphs. The QI and QJ with the label A is in the graph if and only if delta of the Q comma A is consist of the QJ. Next, it comes to the here strings. A string of input symbols. In the last session, I explained. A string means it is consist of the set of letters, all the alphabets. That is a group of elements, group of the alphabets. So that is one of the set. From that, it is the transitions will be the having, that is a stage to another state. So that is string of input symbols. That is a string finite atomic. String of input symbols is accepted by the NFA, non-deterministic finite automata. If there is some sequence of the possible moves, that will take the mission to final state of at the end of the string. So in this finite elements states, it is the final state at the end of the string. Yes, string that is not accepted by the mission only if there is no possible sequence of moves by which the final state can be the reached. It is a considering example. It is a non-deterministic finite automata. It is a transition graph is comes to the here Q0 to Q1 equal to how much A, and similarly Q1 to Q2, similarly Q2 to Q3. In these connections, it will be represented, that is all are the A. In this, it describes NFA, which is R are the two transitions labeled A for the state Q0, state Q0. So here one state it is moving to the here state Q0 and Q4. It will be the going to the two distributing labels. That is called as a here. Whenever it will be the one node to, it will be connected to the two or more nodes. It is comes to the non-deterministic finite automata. Next, here also it is a non-deterministic finite automata. It will be the clearly it will be go for the Q0 to Q3 as well as Q1. It is will be the transition diagram will be the represented. And here both are the different, but it is having that is a Q0 itself also the one, and some another it itself is not one. So here multiple connectivities we have. So it is a non-deterministic finite automata. Transition diagram is consist of the non-deterministic finite automata since there are the more than one transition labeled from the 0 and 1 out of Q0. So here Q0 itself it is a two or more. It is a 0 0 is going on and 1 1 also going on. So non-deterministic finite automata. NFA accept that is the string here 0 1 0 0 1 because there is a sequence of the transition. 5 minutes late. Here transitions through the state Q0 Q0 and Q0 Q3 Q0 Q4 labeled and 0 comma 1 comma 0 comma 0 comma 1 Q4 is one of the final state. The particularly NFA accept all the strings with either two consecutive zeros or the two consecutive ones. The transition labels delta, it will be represented. Here connectivities, it is a zeros are the double. Here Q0 Q3 and one also Q0 Q1. So it is a Q0 will be represented zeros and ones, so that it is a non-deterministic case. It is only one will be there. It is comes to the deterministic case. The sequence of the states will be represented. Here connectivities from the Q0 to Q3 is a 0, no connection, and Q0 to Q1 is the 1. That is the first is over. Next I am going for this transition Q0 to Q1 is more. Then again I will take that is a 0 0, means it is a 0 0 1 2, it is a Q4, it is moving. So I want to go for the Q0 to Q4 directly. I can take this is kind of the label. So when it will be the going that it is called as a sequence of the states. We called as a sequence of the states for input strings. Now with the transition delta of the Q0 comma 0 is unspecified, and this is the interpreted as a transition to the empty state, empty set. Example, the NFA, non-deterministic finite automata, used the example 15.3.2 previous one, and find the delta of the 0001. He will ask. The diagram is the same. So here delta of Q0 comma 0 is a V0 comma 0 1 equal to delta of the delta Q0 0 comma 1. So delta of the Q0 comma 1 union delta of the Q3 comma 1. So it is equal to the Q0 comma Q1. Since it is a delta of Q3 comma 1 equal to empty. Similarly, we can compute delta of the Q0 comma 0 1 0 and Q0 comma Q3. Here, whatever the computations we can get from the here 0 1 0 1, what are the connectivities we have in between the states, so that will be the we can be right into the set of the, so it's the representation Q0 comma Q1 comma Q4. It is a non-deterministic finite automata. Now here the strings, I mean that is a set of the string elements. So here we can go by నెక్స్ట్ అందులో ఇంకో క్వశ్చన్ ఉంది. Now the set of all the strings epsilon set, and it is our strings set. It is it means that it's the alphabets set. A string means it is a collection of the characters. All the characters we can be represented the one set. That set will be the belongs to the epsilon star. Epsilon star means it's the set of characters only accepted by the non-deterministic finite automata is called as a language accepted by the NFA. Language accepted by the NFA. Here, drawing of this, it is a language is a grammatically represented as a here delta Q, F sigma, A, B. So, like here, we can be represented, and a group of the elements will be the command. So, characterize the strings. The drawing that is the state diagram for the NFA, for which the state table is given below. Characterize the strings is accepted by the NFA, for which the final accepted state are the Q1 and Q2, or the state starting state is a Q0. Hence, the obtained the language is accepted by this NFA. Next, Q comma delta is a Q0, Q1, and Q2, and sigma A comma B. And Q0 comma Q1 is a set, and Q2 is one set, and phi and Q1 is one set, and Q1, Q2. Solution is here like that he will give in the problem itself. Now, do it. Now, solution. So, that is also another problem. Now here, solution. Here, I am taking the connectivities. Once again, you see here, what do you mean? That means it is a diagram representation, Q0 to Q1 and Q1 to Q2. What are the connections we have that will be represented in the diagram? The diagram is called as a state diagram. A table he will language he will give, that language is we will be constructed into the non-deterministic automata, finite automata construction, that is called as a state diagram we call. So Q0 itself of having that is a A, and here what are the connectivity itself we have, that all will be the represented here. This is called as a state diagram. State diagram means we have a connections. Next, a string is consist of any number of the A's, then the NFA can be shifted to the accepting state and Q1 starting from the Q0. If a string is consist of the any number of A's followed by the number of B's, then the NFA can start from the Q0 and reaching the final state is the same. It is a what you have designed from the state diagram from the about table. Table means it is a Q0 to Q1. What is the distance? A is having the connection. It is represented Q0 to with the direction of the Q1. Sometimes Q0 to Q0 also representation diagrams here. So that is what you are stating there, how the connections are happen. Total theoretically you should write. That is called as a string consists of the any number of A's, then the NFA can be shifted to the accepting state of the Q1 starting from the Q0. If a string is consist of the any number of the A's followed by the any number of B's, then the NFA can be start from the Q0 and reach the final state at the Q. If a string consists of the number of any number of A's followed by the A string by B and then followed by the any number of A's, then NFA can start from the Q0 and reach Q1 or Q2. Then the strings accepted by the NFA are A power M into B power N. M is greater than or equal to 1, N is greater than or equal to 0. And A to the power of M into BA whole to the power of N, A, comma, M greater than or equal to 0, N greater than or equal to 0. The following the acceptability we have, this kind of the diagram. That will be the SAQ bottom we explained. Here, sometimes he will give that is a diagram. Now, the transition diagram of the NFA is given by this is and determine whether the string 010 means it is a representation of the connectivity, so it can be represented accepted by this NFA. NFA with the most means it is a sometimes situations it is using that is a allow from the transitions by empty input also the transition will be the accepted. That is called as such transitions are called as epsilon transitions, and epsilon transitions causes of NFA to move from the one state to Q state to P. Then whenever that is the NFA reaches that is the state Q is in some competition, it can be the immediately processed to the state without the consuming any further input. Next, it is a non-deterministic finite atomic with the epsilon moves is the quantum capital M equal to Q comma sigma delta comma Q naught comma F with the components as defined. Now here we can take the quantuple. It is a M equal to Q comma F sigma and delta Q naught and F with all the components as. Here transition states will be mapped to and bracket epsilon to 2 power Q. Here state states are connected to that. It is a P I Q delta, that is a Q star, and sigma U epsilon tends to 2 power Q. This means that it is a delta of the Q comma A will consist of all the states P such that there is a and a transition labeled from Q to P where A is either epsilon R symbol in sigma. This is a definition of non-deterministic finite automata theory with the epsilon moving for the quantities, quantites. And whenever the NFA moves from the transition graph is given below, Q2 is the final state and Q naught is the starting state. So here Q naught is the starting state 0. It moves from the Q1 to Q2. Now, drawing of the states will be the state table which should be represented. He asked that the final find the Q naught is a state table. So here Q naught state table, what we have that we can be right 0, 1, 2 epsilon. Q naught, Q1, Q2. Here, what are the parameters in between? We have a Q naught, Q1, Q2 in the sequence. Similarly, it is a delta distances also 0, 1, 2 epsilon. So here we can take that it is a what are the state table is connected that will be represented. Here in this it is a Q naught and phi and Q1. And another is comes to the Q. So here this is a connectivities are not there, so it is called as a empty sets. Now in this empty sets we can be represented Q naught to epsilon. Now definition of that, it is a string is said to be accepted by the NFS minus epsilon if the transition, if there exists at least one path, the path that start at the initial state and ends in the one of the final state. The path formed contains states with the transitions from epsilon transitions and or non-epsilon transition. In order to identify the state in the actual path formed with the epsilon transitions, we introduce a notation here epsilon closure. Definition, it is a epsilon closure of the given state Q is defined as the set of all the states P such that there exists the path the Q to P labeled. Next, it is coming to the definition is when we will be representation epsilon to closer to P and where P is the state of the state is defined as a union and closer Q and epsilon. In between that, it is a Q belongs to P. So it will be the defined and extendable transitions functions delta 2 and function delta that maps from the Q class to epsilon star tends to 2 power Q. Delta of the Q comma epsilon and epsilon closer Q and for the W belongs to epsilon star and A belongs to epsilon and delta star Q comma WA. It is a closure. P equal to P such that for some R in the delta star Q W and P is in the delta of R comma A. We also extended delta and delta star to sets of the states by the delta of R comma A. So union of Q belongs to R delta of the Q comma A. This is a non-deterministic automata. And in the exam point of view, he will ask the question: find delta cap of q naught comma epsilon. Value is like what is that? And q cap q naught comma 0. What is the delta cap q naught comma 0 1? What is the value? So that it is NFE with the epsilon moves here. Solution point of view. First, you take from the here 15.3.13. It is a we have a figure. From that, it is a directly we can take the connectivities. It is a delta of the q naught comma epsilon equal to here epsilon is the closer. Second is comes to the here epsilon point of view. Epsilon closer. Here do it fast. Now here delta of here a naught comma delta cap and here q naught comma epsilon I want to find out, and a delta cap q naught comma 0. Delta cap q naught comma 0 1 for the NFA with the epsilon moves as mentioned. So here I am taking the closer connectivities. It is q naught comma 0 and q naught comma 0 1 connection. So how many we have? All the connections I can be connected. So this is you should be remember and write in the examination. This is the important, most important. Next, equivalence of the DFA and NFA. In the theoretically, he will ask in the question, explain about the explain in details of the equivalence of the DFA and NFA. In this computational models, it is a DFM is a uh, uh, deterministic finite automata and non-deterministic NFM is non-deterministic finite automata. DFA is by the definition of an NFA. Each state has a NFA means each state has exactly one output grow under the each symbol. That is called as a DFA. And NFA is by defining that NFA it is the epsilon but with no epsilon motion. So it is a definition of defining the n of A tends to it will be the representation but with the no epsilon modes. So NFA dash epsilon we call minus epsilon we call. And a language accepted by this terminology is called as L of M. L of M. But it is a finite automata and capital M where in the DFA or NFA minus epsilon. Next it is comes to the here both are the equal he mentioned. Here two finite automatas. It is a that is only the our proof. No, yeah, what is that equivalence of the DFA and the NFA? When it will be possible? That is I want to give the here directions. It is comes to the M1 M2. Maybe the different types are the equivalent if and only if and L of M1 equal to L of M2. L of M1 equal to L of M2. Now it is two finite automators M1 and M2. If you take that, it is a two equivalences if and only if L of M1 equal to L of M2. That is if they accepted some languages. What are that illustrations? If we take, let M1 be the DFA and M2 be the NFA. So it is a one transaction from the first one and another transaction from the M2. Both are the equivalence. We will be say that. How it is a possible? It is a transactions. Both must be the same language. So 10 to the power of n such that n greater than or equal to 0. Hence M1 and M2 are equivalences. Since the DFA is in the essence of the restricted kind of the NFA, and it is obvious that any language that is accepted by DFA is also accepted by some NFA. The converse of this, it is every language is accepted by the same NFA. There is a DFA that accepts the same language. Both are accepted by the same languages, but the not so obvious. This is can be seen by the following theorems. So that it is both are the equivalents. That's all. Next theorems will be coming to that. Here let L be the language accepted by the non-deterministic finite automata. Then there exists a deterministic finite automata that accepts L, same accepts L. So M is I am taking that it is a Q. Here language point of view, capital M equal to set is a Q of sigma of a delta comma Q not comma F I will take B and NFA that is accepted the language L. Define the DFA M dash equal to same way it is a opposition of the DFA. So NFA is the opposition of DFA. So that instead of M, I will take the M dash. It is a Q dash, epsilon dash, and Q dash, Q1 dash, and F1 dash. So it is a both the DFA plus the NFA will be the opposite. So Q dash, that is a grammatical representation for that. It is a Q dash equal to how much 2 power Q. The states of the M dash are also the subsets of the set of the states of M. F dash is the set of all the states in the Q dash containing the final state of M. Denote an element of the Q dash by Q1, Q2, so on Qi, where Q1, Q2, so on Qi are in Q. Note that it is a Q1, Q2, so on Qi is a single state of the DFA corresponding to set of the states of the NFA. Take the initial state Q not dash or M dash equal to Q naught, define delta dash equal to Q1 so on Qi comma A. So it is equal to the P of 1 P2 so on Pj. If and only if delta of the Q1 Q2 so on Qi comma A equal to P1 P2 so on Pj. That is a delta 1 is applied to an element of Q1 Q2 so on the Q1 Qj of the Qi. Dash is computed by the application, applying the delta to each set of the Q represented by Q1, Q2, so on the Qi. In the one applying that to the each Q1 comma Q2, so on Qi, that computed to the here finite automata to the connectivities of the here capital M dash equal to how much Q naught. It is the initial state. Delta of dash of Q naught so on Qi equal to comma A. The transition state is A. So P1 that representation Q1A equal to P1, Q2A equal to P2, so on Pj. Now if and only if that will be the separated by the delta, here also we can get the P1, P2. So delta that applied to the element of the Q1, Q2. Q that is computed by the applying the delta. Each set of the Q represented by the Q1, Q2, so on Qi. On applying that is a delta to each Q1, Q2, so on Qi, and the taking the union, we get some new set of the states P1, P2, so on Pj. For this new set of states, we associate P1, P2, so on Pj in Q dash, and this element is the value of the delta dash Q1, so on Qi. A. Now we prove that it is an induction on the length of the input string x, that is a delta 1 of the Q1 dash Q naught dash comma x. So Q1, Q2, so on Qi. If and only if delta of Q naught comma x equal to Q1, Q2, so on Qi. This is obvious for mod x equal to 0, because mod x equal to Q naught and a delta of Q naught dash comma x equal to Q naught. and delta of the Q naught comma X equal to Q naught. Now let us assume that the resultants of the each string of the length n. So it is let A be the representation of the length. So in this hypothesis, it is the resultant will be the let x naught string of the length n plus 1 with A and epsilon. Then it is a delta dash of the Q naught dash comma X. So it is equal to delta dash comma Q naught dash comma X comma A. Now all the representations will be the mixing with the states. Then it is coming to the here delta of the P1 P2 so on Pi or Pj comma A equal to it is a R1 R2 so on Rk. Thus it is comes to the delta 1 to here. Hence the resultant is the string length is also n plus 1. So L of m equal to L of m. Whenever you will ask that is equivalence of the DF and NFA, this theorem as well as previous explanation, both you should be right. This above transaction definition from the definition onwards, if you write, it's a definition. Equivalence of the DFA means this thing you should be right. Definition as well as theorem. Then you will get the full marks. Here 4 marks question, he will use that is the exam point of view. This one, capital M equal to Q1, Q2, so on, QM. This example construct the DFA equivalence to the having. We construct the DFA. Trivially, we can take the delta dash. Similarly, here we can do this problem. Next to Morse and M.Sc, Morse and Meili missions. Last topic. Here, Morse and Meili missions also the same procedure. We will represent one delta. Delta is the output alphabet. We call it as the output alphabet. Lambda also we can take from the mapping of the Q to delta. This is the output association. So in here they can take a lambda into something. So it is a mapping from the Q to delta we can be represented. That is called as a Moore mission. And the Meili mission comes to the here. In this, not only the dot product, it will go for the cross product, means ordered pair of that single 6 tuples. Here delta and lambda also we added. Whereas that is a more missions except lambda, which is a mapping from the Q cross delta to Q cross epsilon to delta. And this lambda will be the ordered pair of the Q comma A. That is comes to the given that is the output of the searching. With that, it is a they can be decided that it is come. Yeah, states of the connectivities between that is a Morse and Meili. These are the examples. Here, truth tables how we know that is a construction of the transition states graph. Here, representation of the transition table. Then we can go for the transition alphabet. This is a overall idea about that unit. Okay, this is overall idea about that. Remaining part we can do study is represented here. This is also important. 15.5.10. Morse and Meili also both are the equal because of non-determinist determinist both are the equal. Here also it will be both are the equal. This is the oral idea. Next we can discuss that is a minimization of the finite automaton in the next class. Here minimization of the finite automaton. We have seen that the earlier sections that will be the possible to have the more than one DFA. Next problem. పర్లేదు చెయ్యి. Here, minimization of the finite automata, we complete. 5 minutes will be there. We can complete. We have seen in this earlier session that is possible to the more than one DFA. If we take that is a single DFA, that is the previous sessions. It is a more than one DFA if we consider that is acceptable the same language. And actually here there are there are the equivalent to the DFAs. In this session, we see how to construct the DFA with the minimum number of the state equivalent to a given finite automata. This concept is a very useful when the DFAs are used to the design of the computer hardware circuits. Minimizing the DFA increases its efficiency by the reducing its number of the states and also the enabled as the determine if the two DFAs are the equivalent. Thus, it is a minimization or optimization of the DFAs. It refers to the detection of the those states of the DFA whose presentation is clearly represented. It is a presence and absence do not affect the language accepted. That is comes to the finite automata. With this effects that is automata without affecting the languages, some of them states can be eliminated. What are that? It means the unreached states can be eliminated, and the dead states or the trap states will be eliminated, and the distinguishable or non-distinguishable states will be the eliminated from the automata. So it can be the represented minimization of optimization. So which is a minimum length we can be with minimum states can be connected that can be identified. This is the overall idea, but it is a total unreached states are the states of the DFA which cannot be reached the state by the input sequence. So that sequence will be the identified by the here. Here representation will be the delta of the P comma W. That is a representation that will clearly belongs to F. Like here we can be represent. The example we can take that this is an unreachable states. These are the various examples for that. Undistinguishable states, so we can be represented. Example also. This algorithm, he will ask it's the algorithm for it is a construction of the minimum automata. Here first unreachable states we should take and eliminate from the DFA. That is a sequence will be the give to the it is a product of Q1 star, Q1 circle to the Q1 Q1 circle to the Q2 circle. So that it is a two separate sets will be the product. It will be the set of all finite states can be represented. Q2 naught means it is a Q minus Q1 naught. So already Q1 naught will be there. So Q1 naught will be there. Total set is a Q from the Q naught. Q minus means it is a subsets we can be taken. That subsets observation will be the here Mollis and Morse will be the discussed. So it is a construction of the pi and pi k plus 1 from the pi k. It is a let qk can be the subset of in the pi k. And the q1, q2 are in the qk. They are the k plus 1 minus equivalent provided by the delta of the q1 comma k and delta of the q2 comma k are the k equivalent. Determine whether the delta of the q1 comma a and the delta of q2 comma a are in the same equivalence class in the pi k. For the every symbol a belongs to epsilon. If so, q1 and q2 are the k plus 1 equivalent, and in the same way it is divided for the q for k into the k plus 1 equivalence classes. Repeat this for the every qik in the pi k to get the all the elements of the pi k plus 1. Consider the phi n for the n equal to 1 to n, so on till pi n equal to pi n plus 1. So that it is the we can get the minimum point. For the required the minimum state automata for the state of equivalences classes the step 4. The elements of the pi n is the present in the transition table and transition graph will be the minimum state of automata. So that we can be represented example form here this one. This state diagram of the diagram and it will be the connections will be the we can represent the two sets combinations. So pi 1 state and pi 2 state. That is the states in between that it is a subsets will be the how we can be transition states will be the connected. That will be the base the based on the graph we can be minimum state can be the identified. This is only the one problem will be there. It is only the important. Next, turning machines. Turning machines means it comes to the only, for example, it is a 7 tuples we have taken that capital M, and where Q is a finite set of the states, and say and neta is a finite set of followed by the type of the symbols. And a symbol is of the data is a blank. It is a sigma subset of neta not included the input symbols. So it will be the represented to the various combinations of the sets. So that is called as a turning mechanism missions. Now in this representations, it is a header writing and how that turning machines will model will be represented. It is a tap recording that is the data of the sequences into the one memory states will be the sequentially it can be stored. So the transition will be the represented is the turning mission representation like that. So Q1 comma Q2 belongs to L. So like it is a sequentially, it will be the all will be the moves from the left to right. So like that, it will be the read and write header files will be the work on in the sequential order. These all are the examples. That's all. In this today class, we discussed about the concept of non-deterministic and equivalence of DFA and NFA, and learn that is about the finite automata models. Mainly, it is a motion missions and mainly missions associated with the state and with the transition respectively. Okay. In the next class, we will go for that is the next grammar for this finite automata. We meet in the next class.
Okay, sir.
Okay, sir. Thank you.
Okay, ma. Okay, ma. Thank you.